The drive in your computer saves and stores your data, everything from documents to photos to software programs. The newer generation drives are solid-state drives. They're gradually replacing traditional hard disk drives because they're compact, more durable, and process information much faster. Just like portable USB drives and camera memory cards, solid-state drives store information on several memory chips installed on a circuit board. Each chip contains highly complex circuitry comprised of electrical pathways 2,000 times narrower than a human hair. To make those memory chips, they begin with a disc-shaped silicon wafer. Silicon is a non-metallic natural element which conducts electricity. It's highly susceptible to contamination, so the production area is virtually sterile, to the point of being 1,000 times cleaner than the air in a hospital operating room. An automated robotic system moves the wafers through more than 800 operations, which take more than a month to complete. Each wafer receives layer after layer of materials, some conductive, such as copper, some non-conductive, such as silicon dioxide. After applying each layer, the machine coats the wafer with a light-sensitive fluid, then flashes UV light onto it through a glass stencil of the electrical circuitry pattern. In the areas where the fluid is exposed to the light, the chemicals break down and dissolve. Where the fluid was shielded from light by the stencil, the materials remain intact, effectively printing the circuitry pattern on the wafer. Chemical baths then wash away the exposed fluid and material. Each 30-centimeter wide wafer yields hundreds of microchips, which now have to be sliced apart. The robotic cutting machine covers the wafer with an adhesive film to hold the chips in place while they're being cut loose from each other. The next machine inserts each clip in a protective plastic housing. Meanwhile, 6 circuit boards at a time enter a machine which applies a thin layer of tin alloy solder paste onto the areas where the memory chips and other components will go. As the boards exit the machine, a robotic arm picks off the components required for each drive from feeder spools and deposits them at their respective locations on the circuit board. This particular model has 8 microchips, each able to store 64 gigabytes of data, giving the drive a capacity of 512 gigs. The circuit boards now enter a tunnel-shaped oven, which melts the solder paste, fusing the components to the board. The brain of the solid-state drive is now complete and ready for the first phase of quality control testing. This machine performs an optical scan to verify that every component on the board is set in the right place. The next machine X-rays the board to verify that each component is securely soldered in the correct location. A later phase of quality control testing will verify the drive's performance. Until now, 6 circuit boards have been attached to each other. An automated router now cuts them apart, and workers insert each board into a protective plastic housing. A slot on the outside of this housing reveals the board's connector, by which the drive links to the computer. Solid-state drives come in different sizes. This particular model is large enough to replace a traditional hard disk drive. However, many models are smaller, designed to fit where disk drives can't, for example, in ultra-slim laptops. Every drive is labeled with its technical specs, model and serial numbers, and so on, along with a barcode for production tracking. Then they plug the drive's connector into a tester, which, after verifying that everything functions electronically, installs the drive's operating system. The drive moves to the next station, where it undergoes up to 60 hours of extensive performance testing to ensure that it stores and retrieves data correctly and at target speed. Packaging is twofold. First, a foil shield to prevent static electricity from damaging the drive, then a carton, and finally, into a shipping box, headed for a destination somewhere around the world.